Let's compare R2 and the xy plane in R3. Now R2 is just our old friend, the xy plane. But remember, technically R2 is the collection of vectors with two entries like this, right? So this is R2. The xy plane in R3, well, it's this plane, right? There is a z-axis in R3, but the xy plane doesn't contain the z-axis, right? It's just the x-axis and the y-axis and the plane that they span. So what are the vectors? So this xy plane in R3 is a subspace of R3. What vectors are in that subspace? Well, you can see all vectors that are in the xy plane down here, their z-coordinate has to be 0. Otherwise, they would poke up out of the xy plane. So the xy plane in R3 as a subspace, it's every vector that looks like x, y, 0. All right, so this is the xy plane sitting inside of R3. Now, both geometrically and based on the entries in these vectors, you can see that these look basically the same. I mean, in our geometric picture, the xy plane, it sounds vacuous when you say it, but in the picture, the xy plane on its own looks the same as the xy plane sitting in 3 space, right? I mean, I've drawn it differently, but that's just to get some perspective on it to make it look 3-dimensional. But it's the same geometric object, right? It's a plane with an x-axis and a y-axis that are perpendicular, so, you know, basically the same thing. And looking at the entries for these collections of vectors, you can see that the entries sort of behave the same way. To specify these entries, you have to specify an x and a y, but that's the same thing over here, an x and a y. And in fact, even the vector operations in these two collections of vectors work the same way, right? To add two vectors in R2, you just add first coordinates and second coordinates. To add vectors in this subspace of R3, you just add first coordinates and second coordinates. You don't have to do anything with the third coordinate because it's going to be 0 no matter what. So even just on a vector operation level, these two collections of vectors look pretty much the same. On the other hand, even though they look so similar, they aren't literally the same vectors because vectors in R2 only have 2 entries. These vectors in the xy plane in R3, they actually have 3 entries. It's true that the last entry is always 0, but that is a third entry, right? So on the one hand, these two collections of vectors are different. They aren't literally the exact same vectors. But on the other hand, they kind of have the same structure, right? You can see that it would be very straightforward to define a linear transformation going from R2 to the xy plane just by sending xy to xy0. And in fact, we could go the other way just by sending xy0 to xy. So maybe the reason why these look so similar is because there's a linear transformation going both ways. And in fact, if you do one linear transformation and do the other, and then the other, you get back to where you started. And same thing if you start over here and do that linear transformation and then this one, you get back to where you started. So maybe that's what really makes these two subspaces look basically the same. It's that there's this cycle that you can do just by following linear transformations and always end up where you started. So for that reason, we're going to make this definition. We're going to describe this situation by saying that these two vectors, these two subspaces are isomorphic, and the transformation between them is an isomorphism. So an isomorphism is a linear transformation from one subspace to another that has an inverse transformation that is also linear. So just for an example, let's show that this linear transformation is an isomorphism. So we can represent this linear transformation by multiplication by a matrix, as with any linear transformation. So this is -2, 3, 3, -5, like that, times AB. Okay, and to know if, so we want to find an inverse an inverse transformation that is also linear. And, we can basically, we can guess what the right transformation is, because it sort of seems like, well, if this linear transformation T is given by multiplication by a matrix, then T inverse seems like it ought to be given by the inverse of this matrix A, right? Stands to reason. So, well, that means, hopefully that's true if this transformation exists, or if this inverse matrix exists. So let's compute this inverse matrix and see if it actually does exist. To compute an inverse matrix, remember we can just augment this matrix with the identity, and then row reduce the left-hand side, and hopefully it row reduces to the identity. So let's do it. Let's see, maybe the easiest way to make this, I don't know, there's no nice way to do it, I guess. So let's just take row 2 minus plus 3 halves row 1. So we're going to get minus 2, 3, 1, 0. And then, now I have to do all this fraction stuff in my head. So this is going to 0 out. And then, let's see, 3 times 3 halves is 9 halves. Minus 10 halves is minus a half. Okay, and then here we're going to get 3 halves and 1. Okay. Now we need to do, I guess, row 1 minus 6 times row 2. Actually, at first, why don't we do just multiply row 2 by minus 2. That'll be easier. So minus 2, 3, 1, 0, 0, 1, minus 3, minus 2. Okay. Hope I did that right. And then now we can do row 1 minus 3 times row 2. So this gives us minus 2 is 0. And then, let's see, minus 3 times minus 3 is plus 9, plus another one is 10, and 6, 0, 1, minus 3, minus 2. And then finally, we'll do minus 1/2 row 1. So this gives us the identity on the left-hand part, and on the right-hand part we get 5, 3, minus 3, minus 2. Okay, so now our guess for T inverse is that T inverse applied to a vector should be just this A inverse, which is 5, 3, minus 2, times V. But look, this is obvious. This is clearly right, because T inverse applied to T of V is just A inverse times A times V, but A inverse times A is the identity times V, but that's V. And then the same the other way, right? T applied to T inverse of V is A times A inverse times V, but that's the identity times V, and that's V. Okay, so we showed that this is an isomorphism essentially by finding its inverse, right? Since this linear transformation is given by this matrix, we found the inverse of that matrix, and that inverse matrix gives us the inverse transformation. All right, for another application, or another use of, another test of our understanding of isomorphisms, is let's show that a composition of isomorphisms is an isomorphism. So suppose we have T going from some subspace V to some subspace W, and then some other transformation going from W to some third subspace U. And let's assume that these are both isomorphisms. so iso for short. These are both isomorphisms. That means that they have inverses. T inverse is going to go from W to V, and S inverse is going to go from U to W. Okay, well, if we're hoping that S composed with T is an isomorphism, what we want to do is find the inverse of S composed with T. Well, what could it possibly be? I mean, it seems like, we can basically guess the right answer. It seems like it ought to be built out of T inverse and S inverse. So maybe it's S inverse composed with T inverse. But this doesn't make any sense because T inverse takes us from W to V, and then S inverse, it should start from V if this composition is defined, but it doesn't start from V. S inverse starts from U. So this composition doesn't even make sense. So what about the other composition? How about T inverse S inverse? Right. So this is our guess for the inverse of S composed with T. So how can we check if this guess is right? Well, we can compose them. Compose our guess for the inverse. Right? This is what we're guessing is the inverse. Compose it with S composed with T and see if we get the identity. Well, look, composition of functions is associative. So this is T inverse composed with S inverse composed with S, composed with T. But S inverse composed with S, that's just the identity function on W. Right? So now this chain of functions, it does T, and then it does nothing while you're in W, and then it does T inverse. So this middle step of doing nothing, we don't need to write that. So this is equal to T inverse composed with T, but T inverse composed with T, that's just the identity on V, which is what it was supposed to be, right? With this composition, we were hoping to get the identity on V, and that's what we got. Now we need to check the other way. So what about S composed with T, composed with T inverse, composed with S inverse? But this is going to work out the same way, right? We can write this as S composed with T inverse, composed with S inverse. T composed with T inverse, that is the identity on W. Yes, W, composed with S inverse. But the identity on W doesn't do anything, so we can just write S composed with S inverse. But S composed with S inverse is the identity on U. But that's what we were hoping to get. So this proves that the inverse for S composed with T is T inverse composed with S inverse. This probably should come as no surprise because, right, if T is represented by the matrix A and S is represented by the matrix B, then the inverse matrix for A times B is A inverse B inverse. And you can see it's following the same pattern here, right? So as usual, matrices and matrix multiplication correspond with linear transformations and composition of linear transformations. I guess one last thing we should point out is this transformation T inverse and S inverse is linear because it's a composition of linear transformations. All right. Well, as with so many other things in linear algebra, there are lots of conditions that are equivalent to being an isomorphism, so let's have a look at some of those. So for a linear transformation from V to W with the matrix A, the following conditions turn out to all be equivalent. So T is an isomorphism, the matrix is invertible. Now this, I don't think there's anything to prove here, right? Our experience on the last slide probably is enough to prove that this is the case. If you have an isomorphism, then the inverse of A is just the matrix of the inverse of T and vice versa. Showing that having an isomorphism is equivalent to your transformation being one-to-one and onto is actually a little bit tricky. So let's suppose we have an isomorphism. Let's show that it's one-to-one. So I'm going to put this over here. So suppose T is an isomorphism. We need to show that it's one-to-one and onto. So if T of V equals T of W, right? Remember, what we want to show in this case is that V is equal to W. That will mean that T is one-to-one. But we have an inverse for T, so we can apply T inverse to both sides on this equation. We get T inverse of T of V is equal to T inverse of T of W. But T and T inverse, they're inverses. So T inverse of T of V is V, and T inverse of T of W is W. All right, so we assumed that the outputs were the same. We proved the inputs are the same. So T is one-to-one. Now let's do onto. So we need to, so let's find V in this equation, T of V equals W, right? Being onto means that there is always supposed to be some vector V, no matter what the vector W is. So, well, we can guess what V is supposed to be, right? Remember, we have access to an inverse for the transformation T. So how could we get that inverse in contact with T? Well, if we just guess that V is T inverse of W, then T of V is T of T inverse of W, and that's W. So we found this V here. So T is onto. Okay, so that shows that 1 implies 3 here. Now let's go the other way. The other way seems like it should be easy, but there's one sort of slightly tricky point that we'll have to be careful about. Okay, so let's suppose that T is one-to-one and onto. Okay, we can define a transformation S from W to V by the following. If T of V is W, then let S of W be V. Okay, now there are two issues with this sort of definition. The first issue is we have to ask ourselves, have we actually defined S for everything in W? Well, we have, because we've made this definition for every vector W where there is such a V. But there is such a V for every vector W because T is onto, right? So this definition does actually define the output of S for every input W. The second sort of delicate point here is, what if there's more than one V that we could have chosen here? Then this definition isn't well defined because, if there was more than one V for which T of V is W, which one is the output? Well, because T is one-to-one, there isn't more than one V that works in this equation, right? Being one-to-one says if you have the same output, the input has to be the same. So there aren't two different V's that would work here. So there's only one possibility for what V is the output here. So this defines a function from W to V, and clearly, S of T of V is just based on these definitions. S of T of V is S of W, but that's V, and T of S of W is T of V, but that's W. So S is clearly an inverse function. The question is, the slightly delicate point is S linear? Right? That's not totally obvious, right? The sort of easy way to come up with a function that you know is linear is to define your function only on a basis, and then extend it by linearity, and then you know it's linear. But this function S, it's not defined only on a basis. We defined it all at once on all of W. So we have to actually check that it's linear, because it's not obvious. All right, so how do you check if it's linear? Well, let's compare S of AV1 plus BV2, right? What we want to check is this the same as S of, ASV1 plus BS of V2, right? We need to check, does S have the property of linear transformations? So we need to check these two things. Well, what we can do here is, remember, we have access to T. So what we can do is hit both sides of it, see what T does to both sides of these. So T of S of AV1 plus BV2. Well, that's, right, T and S, they're inverse functions. So this is just AV1 plus BV2. All right, well, what does T do to the right-hand side here? It's T of ASV1 plus BSV2, but T is a linear transformation, right? We know that T is a linear transformation, so we can use the linear transformation property. So this is ATSV1 plus B times T of S of V2. But again, T and S are inverse functions, so T of S of V1 is V1 plus B of T of S of V2, so B times T of S of V2, and that's V2. All right, so what we did was we applied T to each one of these things, and we got the same result. But remember, T is 1 to 1. So if you apply T and you get the same result, that means the two vectors you started with are equal. So this vector must be equal to this vector. But that proves the linear transformation property for S. So S really is linear. We already knew it was an inverse, so now it's a linear inverse, and that means T has a linear inverse, right? We explicitly wrote it down. So that's the reverse implication going this way. So 1 is equivalent to 3. Now there is one more property that I want to have a look at, which is that T is an isomorphism is actually equivalent to T sending any basis of V to any basis of a basis of W. So let's suppose that T is an isomorphism. All right. So in particular, this means that T is 1 to 1. All right, sorry, let's suppose we have a basis. Suppose that we have this basis V1 through V. We don't know how many vectors are in a basis for V, but let's suppose it's n. So this is a basis for V. Now our question is, when we hit these with T, so let's see, let's let W1 be T of V1, and so on, down to Wn is T of Vn. So the question is this collection a basis for W? Okay, well, that's two questions. First, we need to know, do these span W? And second, are these linearly independent? Well, let's answer the linearly independent part first. So V1 through Vn are linearly independent because they're a basis for V, so they have to be linearly independent. But something that we proved when we were talking about one-to-one functions is that, right, T is 1 to 1, and for one-to-one functions, we know that the image of a linearly independent set is linearly independent. So that means that these T of V1 through T of Vn, those are linearly independent, but those are the W's. So W1 through Wn is also linearly independent. Okay. So now we just need to know, do the W's span big W. So let's take W in big W. Right. The question is little w in the span of W1 through Wn? All right. Well, T is an isomorphism, so that means there is some V in capital V so that T of V is W. Right. T is an isomorphism, so it has to be onto. So there must be some vector V. Okay, but since V1 through Vn are a basis for capital V, we can write little v as a linear combination of our V's, of our basis. So A1 V1 through A n Vn. Okay. Then what is T of V? Well, on the one hand, look, T of V, that's W. That's what we set up here. But on the other hand, V is this linear combination, A1 V1 plus dot 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 plus A n Vn. But T is linear, so we can use the linear transformation property. This is A1 T of V1 plus dot 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 down to A n T of Vn. But what are these? Well, those are the W's. So this is A1 W1 plus dot 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 down to A n Wn. But look, now we've expressed W as a linear combination of W1 through Wn. So that means W is in the span of W1 through Wn. So every vector in capital W is also in the span, but that means the span is equal to capital W. All right, so these W's, they're linearly independent, and they span capital W, and that means that W1 through Wn is a basis for W. And that's what we wanted to show, right? We started with a basis for V. When we hit all those basis vectors with our linear transformation, we got a basis for W, right? So any basis of V gets sent to a basis of W. All right, that implies that, right, 1 implies 4 down here. Now we need to do it the other way. So let's suppose that T is a linear transformation that sends any basis for V to a basis for W. Okay, so let's suppose we have a basis for V. So this is a basis for V. Okay, but that means, by our assumption, that their images, T of V1 up through T of Vn, are a basis for W. So now that we have a basis for W, having a basis for W makes it really easy to define a linear transformation. So let's just define a linear transformation from W to V. It's easy to define such a linear transformation because we just need to specify the values of S on a basis for W, and we have a basis for W. So let's say that S of W1 is V1, and so on, up to S of Wn is Vn. Okay, so this determines a linear transformation. Now the only question is this the inverse? It's clearly linear because we defined it only on a basis and then extended it by linearity. So the only question is it an inverse? But I mean, I'm not going to write it out, but it's obvious it's an inverse because look, on a basis, it just switches inputs and outputs, right? So it's an inverse as a function, but it's also linear because of how we constructed it. So S is T inverse. And then, so now we've shown it the other way, right? We assumed that we have some transformation that sends a basis of V to a basis of W, and we were able to prove that that means that T is a linear transformation. So all of these four conditions are equivalent.